For those who may not already know, discrete event tools like plant simulation let you analyze the operation of an entire department or facility and optimize overall items like throughput, buffer or inventory, sizes, workers, and scheduling. Discrete event simulations are also often referred to as throughput simulation. Plant simulation is overflowing with useful features, but I'd like to point out three of its unique key features. Object orientation provides intuitive use of powerful built-in and custom-made objects that let you build models quicker. Hierarchy lets you structure complex models in an intuitive manner. It also makes it easier for you to make changes without having to tediously rearrange things like other flat-structured products require. Inheritance lets you make changes in one place. All children are changed accordingly. This ensures quality and saves you a lot of time. I'm a past user of several other simulation tools that do not have these features. I'm not a salesperson, but a hands-on user. I personally have found these features to be so powerful and useful that I would not want to go backwards to those other tools. PlantSim's Library Manager is an extremely nice feature that lets you easily add or subtract objects for modeling, analysis, interfacing, etc. to or from PlantSim's class library that contains the set of tools that are available and visible in PlantSim. There are two tabs in the manager. The Basic Objects tab displays all the default basic objects that are available off the shelf in PlantSim, as well as numerous others that can be added at the click of a mouse. The fact that you can have such fine control over the toolkit for your copy of PlantSim proves how PlantSim was built from the ground up in an object-oriented manner. Similarly, the Libraries tab lets you add or delete tools, free or licensed standard libraries, and additional libraries from third parties or those you make yourself. Plant simulation also makes it easy to create your own objects and put them in your own custom library that can easily be distributed over a network. Our next topic covers several libraries that you may find useful. We'll start with energy modeling and efficiency optimization. Energy pain points include rising energy consumption and costs. Also, green is in with consumers and regulators. Additionally, green certifications like the Energy Star seal and EPA regulations and mandates are becoming more important. The solution to these problems has two ingredients. First, dynamic simulation modeling of systems using a tool such as Siemens Technomatic's plant simulation software provides a powerful virtual environment to test and improve a system's design and operations, to address traditional optimization issues such as maximizing throughput, minimizing inventory and buffers, and minimizing labor. Second, while plant simulation always provided a powerful engine to build, analyze, and optimize your processes, the new energy features that were added to PlantSim recently now let you simulate energy consumption and analyze and optimize energy efficiency. Note, the new energy features are incorporated into the base plant simulation product, as can be seen in the new energy tab that's added to the other input-output tabs for standard plant simulation objects that model stations, machines, conveyors, etc. So they are not actually an add-on library, but we are covering these features here since they are so unique and very powerful. And now we have a video of an energy simulation of an LCD TV flat screen production facility. We'll start with a screen tour of our plant simulation model. The source puts skids on the conveyor to the right, which moves skids up to the main assembly line. The main board is placed on the skid at station A1. The display panel is added at station AS3. Other parts are added further down the assembly line. And then the panel goes through quality, localize, inspection, packaging, and labeling processes before being removed from the skid and transferred to the finished product drain, where throughput statistics are collected and displayed. Using plant simulation's powerful traditional modeling and analysis tools, the existing model was optimized for a maximum throughput of 1,976 screens per day. What-if experiments also showed that a minimum of 80 skids was required to maintain that throughput. Since plant simulation now can model, analyze, and optimize energy consumption, we set new goals for our plant to reduce energy consumption without decreasing throughput. The first step is to specify power inputs in kilowatts in the Energy tab of the stations for all its states, including working, setting up, operational, failed, standby, and off. We also specify the transition times between states. Now we'll run the model for one simulated day. We'll run the model slow for a while so you can see everything in action, starting with the first skid being placed on the main line and throughput statistics being collected when the screens are removed from the skids after the packaging line. After one day of simulated time, you can see that our throughput is the optimized value of 1,976 screens that was mentioned before. Since we added energy inputs for our stations and conveyors, the Energy Analyzer's display panel also provides valuable overall statistics, including 1,899.7 total kilowatt hours of energy consumed. Let's take a look at the Energy Analyzer's Show Visualization option. The stations surrounded by solid red circles are the ones that consume the most energy. Hollow red circles indicate the next largest energy consumers. Blue indicates the least energy consumers. And purple is in between. This visualization lets you quickly identify areas where you may want to focus on making potential individual energy improvements. This is similar to using PlantSim's Bottleneck Analyzer to help you to identify the main throughput bottlenecks. Instead of diving into individual station details, let's take a look at the Energy Analyzer's Show Plotter option. This shows kilowatt consumption at any given time. As you can see, from midnight until the start of the one shift we are working at 8 o'clock in the morning, all the stations and conveyors were in operational or waiting state and consumed approximately 77 kilowatts. Then at 8 o'clock, the equipment switched to working state and consumed about 85 kilowatts. During the 15-minute break at 9 o'clock, equipment switched back to operational. Then back to working state until lunchtime. During the 45-minute lunch break, the equipment switched back to operational. After lunch, we're back to working state. At 2 o'clock p.m., we're on a 15-minute break, so we're back to operational. Then back to work after the last break of the day. Then back to operational state from the end of the shift at 5:15 p.m. until the end of the day, since we are only working one shift. After looking at this chart, you may have guessed that we could save energy by switching to standby during breaks instead of leaving everything in the operational state. To do that in our model, all you have to do is check the on-screen Save Energy Standby During Breaks checkbox. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 1,899.7 kilowatt hours to 1,820.9 kilowatt hours. This would result in a nice decrease in your energy bill over the years. Also, we achieved these savings without any decrease in throughput. Let's take another look at the Energy Analyzer Show Plotter option. Instead of being in the operational state consuming about 77 kilowatts during breaks, our equipment is now in standby state instead, consuming only about 14 kilowatts. After looking at this chart, you may have guessed that we could save even more energy by switching to the off state during off shift or unplanned time, instead of leaving everything in the operational state. Since these periods are long, we are switching to off state instead of standby for even more energy savings. To do that in our model, all you have to do is check the on-screen Save Energy Off During Night checkbox. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 1,820.9 kilowatt hours to 819.1 kilowatt hours. And once again, we achieved these savings without any decrease in throughput. Let's take another look at the Energy Analyzer's Show Plotter option. As you can see, during off-shift or unplanned time, instead of consuming approximately 77 kilowatts, our equipment is consuming just about 8 kilowatts. And during breaks, instead of consuming approximately 77 kilowatts, our equipment is consuming about 14 kilowatts. The secret behind modeling these energy-saving measures is the State Transitions button on the Energy tab for our station and conveyor objects. The left side tells PlantSim what to do at the start and end of a pause or break within a shift. Here, standby is specified. The right side tells PlantSim what to do at the start and end of unplanned or off-shift time between shifts. Here, off state is specified. And last but not least, the Power Up Early option lets you power up equipment early so that your equipment is ready and raring to go as soon as working time pops up, so you get no decrease in throughput. Now, if we look at the Energy Analyzer's Show Visualization option, we can see things have improved, but power supply stations 1 and 2 are still high energy consumers, as indicated by the solid red circles. If we look at the Energy Analyzer's Show Chart option, you can see that the power supply area consumes a lot of energy while in the operational state. We can see the details by highlighting the area in the chart. The light green areas for power supply stations 1 and 2 show that these stations consume a lot more energy in the operation or wait state than the other stations. While running the simulation, it appears that the power supply buffer is always full. A look at the buffer's chart shows that it's almost always full with 150 power supplies. Every time a power supply leaves the buffer for the main line, the power supply line puts in one more unit, hence the near straight but jagged line. One potential energy optimization opportunity in this area would be to treat this buffer as a Kanban buffer, where the power supply line feeds the buffer only after it reaches a lower level of contents. In our model, the Save Energy Power Supply checkbox sets the power supply line up so that the buffer is filled at the start of the simulation, and thereafter it's fed only after 50 units are left in the buffer. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 819.1 kilowatt hours to 755.9 kilowatt hours. And once again, we achieve these savings without any decrease in throughput. Finally, if we take another look at the Energy Analyzer's Show Visualization option, we can see things have improved dramatically in the power supply area. Instead of solid red circles indicating high energy consumption, power supply stations 1 and 2 are now purple, indicating a medium level. There is room for even more optimizations, but I hope you've seen enough to see how useful Plant Simulation's new energy optimization features can be. I hope that gave you a good overview of the powerful features that are included now for energy. Our next topic covers the Food and Beverage library and the recently added built-in fluid objects. To visualize and simulate your food and beverage process, the Food and Beverage library provides several industry-specific modeling objects. 2 source objects introduce fluids and solids into the simulation according to a user-defined schedule. The tank objects holds fluids. The stirrer tank is based on the tank but also includes a processing time to simulate stirring. The mixer is a special tank that can process both liquids and solids and mixes them together. The filling object is another specialized tank that consumes liquids and produces solids that represent filled cases like bottles or filled molds. The diverter singularizes products that have been filled into forms by the filling object. The palletizing object loads products onto pallets. The storage object stores pallets. It optionally lets you directly enter truck orders according to delivery dates. Finally, there are several moving units which move through your process, including mass moving unit produced by filling, piece produced by the diverter, carton to put products in, pallets contain cartons, forklifts move pallets, and trucks make deliveries. As you may know, discrete event simulation tools like PlantSim include features that let you analyze your facility, like locating bottlenecks, and optimize it quickly and safely by playing what-if games that let you test proposed improvements on your computer. The Food and Beverage library adds to this already powerful arsenal of built-in powerful tools. Visualization of your process helps to understand and analyze your process by showing flows through pipes, tanks filling, and emptying. Bottlenecks like a tank being empty for too long can often be pinpointed by just looking at your simulation run. On-screen statistics can include overall data like total pallets produced and number of objects delayed, as well as detailed statistics for individual objects like the contents and status of a tank and its maximum capacity and current capacity. Time and state graphs are a great way to pinpoint problem areas. For example, a station waiting for material for too long. Data tables like truck orders for a storage object let you see the details for every delivery, like the exact date and time. The scenario control lets you play what-if games by specifying different data sets for mixers and truck orders. PlantSim's built-in tools can also help to analyze and optimize your process, including the experiment manager that can automate the running of all the scenarios that were set up in the scenario control, as well as varying other parameters. The bottleneck analyzer can help you to pinpoint bottlenecks, and the Sankey diagram lets you visualize the flow of fluids and solids. The thicker the line, the greater the flow. In the example shown, you can see that more cacao than sugar or milk powder flows into the mixer. Our next quick demo video will quickly show you several of these objects in action. This video shows a PlantSim model of a chocolate factory in action. As you can see, visualization is really nice. You can see raw materials flowing through pipes, tanks filling up and emptying, stirrers stirring, mixers mixing, the filler filling, the diverters sending individual pieces to be wrapped, put in cartons, and cartons put on pallets, then stored and shipped. This screen summarizes the results of 4 what-if scenarios that were run. Throughput was boosted from 335 to 516 pallets per day. Okay, now recently, PlantSim includes fluids objects that let you model food and beverage facilities without the separate food and beverage library that we just covered. As you can see in the example model shown, like the traditional non-fluid objects, the fluid objects like tanks, mixers, and pipes can be viewed in 2D and 3D with the same color coding of ingredients. Both the objects in the add-on library and the new built-in fluid objects model food and beverage facilities. Since each one has a different approach that different types of users may prefer, PMC still supports the add-on library. For example, Plant Simulation's new fluid objects include a unique materials table shown at top where all base and intermediate ingredients and final products are specified, including their on-screen color coding, in one central table that other objects like mixers refer to, while the food and beverage library's mixer objects specify ingredient details within that object, as shown in the mixer's end product table at the bottom of the slide. If you decide to model your food and beverage facility with PlantSim, PMC can help you decide which approach to use. The cool thing is that you have a choice. PlantSim also has several material handling objects. Many of them are not available in most other products. We'll show you several of them, including ones that are already in the default class library toolbox and others available in free libraries from PlantSim's library manager. The multi-portal crane moves in 3 directions and can pick up a part from anywhere and move it anywhere. It can run on rails on the floor or on rails attached to the ceiling. Several cranes can run on one set of rails too, as shown here. Note, for tools that don't have this object, Modeling one or more cranes can vary from relatively simple to difficult to nearly impossible. So black boxing the behavior of cranes could possibly result in inaccurate simulations, especially if they are the main bottleneck. This could lead to bad and or costly decisions. The same holds true for the modeling of a pick-and-place robot. The pick-and-place robot rotates to a station, picks up a part, then rotates to another station and places it in that station. In products that do not have this object, a simple pick-and-place movement can be modeled with a station object. This black boxing is okay statistically, but does not provide the visualization that is becoming more important for communicating to others how your facility works. And if there are several pick-and-place locations, then it's very difficult to model without this type of object. The turntable directly models the actions of a turntable, including time to move a part on and off, rotation time, and rotation angle. The turn plate is another unique object that is similar to the turntable but more complex, since it also ensures that the part is oriented as specified when the turn plate rotates to its destination. This is useful for modeling situations like ensuring that a barcode can be read by a scanner. The angular converter is another unique object that moves parts perpendicularly while maintaining the orientation of the part, instead of rotating it as in a regular perpendicular move on a conveyor. It moves along its length in one direction and its width in the other. I recently had a project that had several of these cross transfers on the plant floor, including different speeds to move in the two directions. Without this object, I would have had to resort to modeling tricks or make a custom object to simulate this. The converter is yet another unique object. The part either passes straight through in the conveying direction or is, for example, lifted onto a laterally moving transport level, then conveyed laterally to the left or right. You may or may not need any of these objects, but they are quite common in the real world, and if your project has those, it's really nice to have these extra objects. The cross-sliding car is mainly used for moving parts from one conveyor to another. Parts enter from left or right, then move across an aisle, for example, and then exit on the left or right. Our next topic is virtual commissioning. Setup and ramp up of the systems implementation for robotics and automation is called commissioning. Traditionally, this step is done after the physical system is built on the shop floor. Tecnomatic's virtual commissioning lets you test and optimize commissioning during the planning and design phase instead of during setup and ramp-up time in a virtual environment that takes into account equipment like robots, PLCs, conveyors, light barriers, etc., without any risk to the real facility. Doing this cuts typical setup and ramp-up time from 4 to 5 weeks to 1 to 1.5 weeks. In other words, time to job one is reduced and problems can be addressed before production starts. Besides being a very powerful genetic discrete event simulation tool that could optimize an entire facility without including commissioning, Tecnomatic's plant simulation's virtual commissioning tools address overall factory issues. This ensures that the overall material flow and operation of a facility works smoothly with components like PLCs, conveyors, light barriers, etc. The OPC commissioning interface lets PlantSim send and receive control logic signals to and from the PLCs. The photo shows a typical setup. On the left is the control panel for the PLC. On the right is the plant simulation model. This is an ideal setup since the PLC is not yet connected to the plant floor, so you can check out and tweak your control logic virtually before going live in the plant. One of my clients used it to check that the PLC control logic worked for their factory conveyor system, which had numerous light sensors and stops along the way where parts would wait for certain conditions before moving on. They were especially concerned about an interesting past problem where a standalone plant sim-like discrete event simulation showed that their control logic worked. But when the plant was built, deadlock conditions occurred where everything was stuck. The problem was that the simulation implemented slightly different control logic, so the problem didn't occur in the simulation. Now they can interface the plant sim with the PLC so that the exact control logic from the PLC controls the simulated stops on the conveyor to ensure accuracy. While plant simulation addresses overall factory commissioning issues, Process Simulate product addresses cell and line level issues. Besides being a very powerful generic tool that can optimize a work cell's robotics, programming, and ergonomics without including commissioning, Technomatics Process Simulate's virtual commissioning tools ensures that automation equipment like robots work smoothly with control components like PLCs. Our next topic, the Value Stream Mapping Library, lets you build, visualize, and analyze your process in value stream mapping format that displays standard VMS icons. Our demo video will show how to use the Plant Sim VSM model to optimize the process. Hello, this is Ray Pashadlo from PMC. I'll be showing you a demo of the VSM library that combines the static VSM methodology with the dynamic behavior of a Technomatics plant simulation model. We'll start with a quick tour of our Technomatics plant simulation value stream model of a simplified desk assembly plant. As you can see, the VSM library uses standard icons to represent suppliers, customers, transportation, inventory, and processes. The blue lines show material flow. Orange shows information flow. At the upper left, Supplier 2 provides the legs for our desks. Transport 2 below it moves 40 legs to Inventory 2. The number below shows how many legs are in stock. It's 0 now because the simulation has not run yet. Supplier 1 provides the raw material for the desktops, which are made out of wood. Transport 1 moves 10 wood units to Inventory 1. Our assembly line starts with the Make Tabletop process, which removes wood from Inventory 1 and turns it into a tabletop. Next, Assemble Desk removes 1 tabletop from Inventory 3 and 4 legs from Inventory 2, then assembles them. Next, the Finished Desk process removes 1 desk from inventory, then stains the desk. Note, during a simulation run, the number below Finished Desk will show the total throughput so far. Also note that the on-screen display of other input and output parameters can be easily switched on and off by you. No programming required. The assembly line ends with Pack 5 desks, which removes 5 desks from Inventory 4 and packs them up for shipment. Note that the number beneath Inventory 4 is 20. That was set with the initial stock optional input parameter. This lets us easily set up a plant's initial condition. Last but not least, Transport 4 moves the 5 desks to the customer who sends out orders and triggers production. Like everything else here, no programming is required to model this. Note, what you've seen so far is no different from a traditional static value stream map. The next slide will show how to use your value stream map to leverage the dynamic power of a Technomatics plant simulation model to go beyond what a static VSM can do for you. This is our screen after simulating 10 24-hour days of production. Note that 6,781 desks were finished. This would probably be the first problem you would notice since it's far below expected production. Also note that a desk is currently being finished while another one is being assembled. You can tell from the icons in those 2 processes. After seeing these results, you would probably want to locate the main bottleneck. There are several analysis tools to help you do that, like the analyzer. One place to start is with the analyzer's relative occupation button. This tool gathers time and state percentages for all processes. In this case, one problem is obvious. The finished desk process is down or failed for a large percentage of time. You discover that the hotshot bean counter who got a promotion for saving money got what he paid for, a cheap machine which goes down 50% of the time. Before presenting your case to replace that piece of junk with the same type of perfect equipment as the other processes, you arm yourself with proof of what that can do. First, you spend about 5 seconds to change the availability of the finished desk process from 50% to 100% since your preferred supplier's machines are expensive but perfect. Your what-if game pays off. Throughput skyrocketed from 6,781 to 11,688 desks. When you present this to your management team, Mr. Hotshot suggests that buying a second cheapo machine will do the trick for less money. But you soon wipe that smirk off his face. How? By using your Technomatics 3D factory CAD model to show that another machine cannot fit in the building because a load-bearing post and a steam pipe are in the way. Worst of all, the coffee machine would have to go too for you to look for more improvements. So you take a look at the updated relative time chart. All that yellow waiting time represents room for improvement. Perhaps it's a supplier or transport issue, or maybe you can get your customer to order more frequently, or find another customer. Your VSM model makes it easy to try your ideas out on the computer before you invest in anything. One more thing you would probably notice, there are a lot of units in inventory 1 and 2. A look inside the inventory over time chart provides details. Obviously, there is plenty of room for improvement. We hope you enjoyed this story, and like all good stories, it has a happy ending. Everyone at your company, except the hotshot, lives happily ever after. Okay, our next topic is bottleneck analysis. This shows you how to pinpoint bottlenecks, areas ripe for improvements through what-if experiments. There are several ways to break bottlenecks and increase throughput. Which ones that are possible and cost-effective for your company depends on your unique situation. For example, if your existing system or design is not optimized, sometimes a relatively simple improvement can make a dramatic increase in throughput. At the other extreme, if you are highly optimized, you might have to implement several improvements sprinkled throughout your system to get a decent throughput improvement. One possibility is to redesign your process to improve efficiency. For example, moving a station closer to a source of resources like parts, tools, or workers, automating an inefficient manual operation, or moving some work from one station to another. Decreasing the processing time of the bottleneck can sometimes be done if it's possible to do and or doesn't affect downtime too much. Purchasing a faster machine is also a possibility. Similarly, decreasing the bottleneck's downtime or repair time can sometimes be done, perhaps through scheduled off-shift maintenance or purchasing a more reliable machine. If a setup is required at the bottleneck, you can look into decreasing that time, perhaps by adding another worker, streamlining the setup process, or purchasing equipment that requires less frequent or easier setups. If the bottleneck has a high rework and or scrap rate, you can look into decreasing those by purchasing more reliable equipment, switching from a manual to an automatic operation, or perhaps changing your process. If the bottleneck cannot be improved enough and space permits, adding a second parallel station may do the trick. If the bottleneck stations require workers, you may be able to speed things up by adding another worker to a shift or adding a part-time shift with fewer workers. Similarly, you might be able to increase throughput by increasing buffer size. If your process includes the production of different models or types of products, then changing how they are scheduled may increase throughput. Technomatics Plant Simulation is the perfect tool to help you to not just optimize your system through what-if games with the above possibilities, but to identify the main bottleneck in the first place. As you may know, optimizing a non-bottleneck is a frequent and often costly mistake, so bottleneck identification is also very important. At worst, PlantSim can verify that your system is already highly optimized and that further improvements may not be worth the cost. And it's a wonderful way to teach or show others how your facility operates. So, how do we find a bottleneck? You look at the simulation output statistics like percent working and percent block and look for clues. You could look at the detailed statistic reports of individual stations as in above. In the demo, you'll see other plant sim tools that help pinpoint bottlenecks even faster. One clue of a bottleneck is a station with the lowest block time. Another is lowest waiting time, also called starve time. Highest working time. Upstream buffers mostly full. Downstream buffers mostly empty. Upstream workstations blocked. And downstream workstations waiting or starved. Okay, it's time for a video of a demo model running that includes a lot of PlantSim's powerful material handling objects, as well as a very nice bottleneck analysis through optimization features, like time and state charts, Sankey diagrams, bottleneck analyzer, and the experiment manager. I'll be showing you how standard and custom objects are used to build a plant simulation model, how bottlenecks are identified, how throughput is improved, and how 3D visualization can be added to a model. For those who have never seen plant simulation before, the class library at the left side organizes built-in and custom objects, including simulation models, into Windows-like folders. The toolbox provides a quick way to access the standard built-in objects, or they can be dragged from the class library into the model, like adding a source to bring parts into the model and a single proc to process the parts. So can custom-made objects, like the object used to model the stations in our demo, which are represented by a custom light green rectangle icon that displays the number of parts that have been processed below the icon. A similar gray-colored object models the buffers in our demo, and the drain collects data and displays the total number of drill collars that have been produced. In this demo, we are making 4 different drill collar products, each one represented by a moving unit with a custom sized and colored icon. Products are scheduled to be made randomly according to the percentages that you enter in the second column of the Excel-like product schedule table object. For example, drill collar type 2s will be randomly scheduled 40% of the time. Similarly, the station data table lets you specify the availability and setup, processing, and mean time to repair times for all stations in one place. Both our input tables were configured to transfer these values to the individual station objects automatically whenever the table is closed. This saves time and ensures data quality. If this data was not in a table, you would have to enter it manually inside each station object, a slower and more error-prone process. Additionally, the table makes it easier to double-check the data and to show it to others. Three cranes move the drill collars from and to the stations and buffers. Crane Portal 1 moves on the bottom set of rails, while Portals 2 and 3 move on the same set of upper rails. As you can see, PlantSim offers the option of having more than one crane move on the same set of rails, a common scenario in the real world. At the bottom of the screen, 5 mere mortal humans are walking side by side, followed by Superman. They are walking on the gray footpaths to their favorite work location. Note that footpaths, like conveyors, can include straight, angled, and/or curved segments. Workers are color-coded. They are green while walking or working and blue when they are waiting for work. The pick-and-place robot moves drill collars from the source to the turntable, then to buffer 1. Note, the pick-and-place robot can be configured to move to several pick-and-place points, not just 2 points as in here. Crane Portal 2 moves drill collars from buffer 1 to the Peel, Gag, and Sonic stations, then to buffer 2. Another unique material handling object, a cross-sliding car, moves drill collars from buffer 2 to buffer 3. Then Crane Portal 1 moves drill collars from buffer 3 to the appropriate boring station, which depends on the type of collar. Each one has a dedicated boring station. This shows the flexibility of the crane object's control logic capabilities. Since there's a fictional beam in the way, a crane can't move to the boring one station. So Superman comes to the rescue to move the heavy drill collar type 1 from boring 1 to grooving 1 and shows off the part carrying option of the worker object. Another unique material handling object, an angular converter, moves drill collars from buffer 4 to buffer 5 while keeping the drill collar orientation the same by not rotating it. Crane Portal 3 moves drill collars to the honing, mag testing, and polish stations, then to the drain that represents the end of production where statistics are collected. Now let's run the simulation faster until 30 days of production have been completed. This shows how simulated time is compressed by plant simulation, allowing you to get results very fast. Statistics for each type of drill collar automatically appears, including mean time in the system and throughput. The drain shows that a total of 246 drill collars were made in 30 days. Now let's analyze the simulation to locate the bottleneck. Just looking at the screen shows that there is a problem after buffer 3, which has 441 drill collars in it. The Sankey diagram is a useful option. The extra thick flow line before buffer 3 also indicates that there is a problem after buffer 3. The Bottleneck Analyzer's Analyze option displays many time and state charts above each object. The large amount of failed or downtime shown by the red bar above grooving 1 indicates that grooving 1 is the likely bottleneck. The time and state chart provides another handy view of the output data. The yellow portion for boring 1 shows that it is blocked a lot because grooving 1 is failed or down a lot. The Bottleneck Analyzer's ranking option ranks all objects according to user-specified criteria. Here, grooving 1 is high on the list with high disruption or failure rate, verifying that this is the likely main bottleneck. Now let's play what-if games with the main bottleneck to see if we can increase throughput. To decrease the downtime percentages for grooving 1, we could change its availability in the station data table to various values and run the simulation for each value to see the effect on throughput. But let's automate this process instead. The experiment manager allows us to automate the what-if process. Here we are setting it to vary grooving 1's availability from 100 to 20 in 10% increments. Just press Start to start the 9 experiments and relax while the availability is changed, the simulation run, and throughput recorded 9 times automatically. You can see which experiment is being run in the current experiment field. After all the experiments are run, a nice HTML report automatically appears. It includes a screenshot of the model, throughput statistics, etc. This table shows the availability percentage and resulting throughput for each experiment. The original values are in experiment 9, whose throughput is 247 drill collars per month. At 50% availability, throughput is increased to 585 drill collars per month. 60% availability gives us just one more drill collar, and increasing availability any higher does not increase throughput at all since grooving 1 is no longer the main bottleneck. You have the option of creating a separate 3D view of the simulation. All you have to do is press the 3D button. A separate frame or window opens with 3D equivalents of the 2D icons, which represent the modeling objects. Cranes can be set up to either be suspended on rails or floor mounted. As you can see, they have true 3D motion, which is always simulated even in 2D, but you can't see the third dimension movements in 2D. You can make the 3D view prettier by exchanging the default 3D icons with nicer ones in the built-in library or import other icons. This simulation example that is included with PlantSim uses a slick trick to quickly build a gorgeous 3D visualization. Clicking on the floor highlights the secret in green, which shows one single JT file produced from FactoryCAD that was easily imported into this PlantSim model. Then the 3D icons were moved to their appropriate 3D locations. Now we'll discuss PlantSim's powerful hierarchy, reusability, and inheritance features. The cafeteria and gym at lower right is a hierarchical object that will open now. It contains modeling details that cannot fit or that we don't want to show at the top level. Optional animation points were created to let you see the workers who are in these rooms. The small black triangle in the lower left area of the cafeteria and gym object is an interface object. This is how PlantSim allows parts and workers to enter and exit an object. Since the cafeteria and gym is a reusable object, we can drag as many children objects that we want into this model or import it into other models. Inheritance means that we can make changes in one place. Here we are changing the color of the icon used for the object used to model the stations. This is not just a cool feature, it's a time-saving feature that allows you to quickly change all the children of an object in one step, instead of tediously making the same change in each child. Finally, I'd like to show you the worker chart, which shows the percentage of each state that all the workers were in. At first glance, it looks like Superman does hardly any work compared to the other workers, but the other workers fooled the system by, quote, working in the cafeteria and gym all day long, while Superman did his job whenever needed, like any decent superhero would do. Okay, before we take questions, we'll look at the recent major plant simulation features and provide some helpful tips. Plant simulation has a relatively new 3D library with smart objects and improved 3D capabilities. This includes improved appearance of several modeling objects, including those here. Although most engineers and analysts only require 2D to analyze and optimize a facility model with plant simulation, 3D is getting more popular for communication purposes, especially for presentations to managers and executives. So these 3D improvements can be very helpful. If the new default 3D graphics are not close enough to the equipment at your location, they can be easily replaced by importing 3D graphic files in several formats used by the major 3D CAD tools, including JT and step files. Version 13 of Plant Simulation had a great new worker object, the option to have a worker walk freely within an area instead of along a footpath object. Before we show this, we'll review PlantSim's powerful set of other worker options. The simplest way to model a worker is to have them work remotely option. That has them work remotely from the worker pool. If worker travel times are very short compared to the cycle times, this is a great way to quickly model workers. The worker is color-coded as shown at top. Blue indicates the worker is not working. Green indicates that the worker is currently working at a station that is working. Like the work remotely option, the beam to option does not model walking time, but it shows the worker working at a workplace object that can be positioned anywhere on the screen. The walk along footpath option lets you model the time it takes for a worker to walk from one place to another. In 3D shown at right, the worker's legs move while walking along the gray colored footpath. Another powerful option is the ability to have a worker carry a part from one station to another in both 2D and 3D. The new Move Freely option lets the worker move freely instead of along a footpath. The worker automatically takes the shortest path from one workplace to another unless there is an obstacle in the way, like a pillar or a pick-and-place robot. The new barred area option on the 3D tab lets you create an obstacle that is round, rectangular, or rectangular without hatching. Besides barred areas, any modeling object that can be specified as an obstacle for the worker. We have a really cool short demo that shows a worker working freely around obstacles. This video shows off Plant Simulation's worker carrying a part and worker moving freely options in action. PlantSim's event controller has been slowed down so you can see the details, like the worker's legs moving while walking. As you can see, Here, one worker works at 3 stations during their cycle times and also carries finished magenta-colored parts from station to station. Note that, similar to many stations in modern factories, the single proc object that represents the stations have colored-coded lights. Green means the station is working, yellow means work is done and that the part is waiting to be moved to the next station. Orange means the station is waiting for a worker. As you can see, the worker automatically takes the shortest path between stations and walks around the 2 obstacles. In this case, the obstacles are a pick-and-place robot's work perimeter and a barrier indicated by the red-colored hatched rectangle. In conclusion, being able to work freely instead of along a specified footpath is a new, unique, powerful feature that provides you with yet another way to quickly model workers.